Good evening everyone, good evening. Good evening. I welcome you all again to JEE Enthuse. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if I'm perfectly audible and visible to everyone. Yes? Let me know fast in the chats quickly if I'm perfectly audible and visible to every single guy. Hello Kamal Raj, hello PC, hello Aisha, hello Priyadarshini, hello Chilaka. Welcome everyone. Hello Harishma, hi R Ramu. Hello Ashwarya. Welcome back all my lovely students, welcome back. Just quickly let me know in the chats, give me some green signal from the chat so that I'll get to know that I'm perfectly audible and visible to everyone. Yeah? Alright guys, just give me a second, we will be starting. Just give me a second. Just give me a second guys. Alright, so as you all must be knowing, tonight we are going to have a session on chemical bonding, right? We'll try to do almost some 40 to 50 questions from the chapter chemical bonding, right? Okay, and let's try to master a few important concepts from this particular chapter with the help of questions. Perfect. So before starting tonight's discussion, the ones who have just joined in, the ones who are new to the channel, let me quickly introduce myself. So people, my name is Wassim and I'm your chemistry master teacher right here on this JEE Enthuse channel, right? The ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this JEE Enthuse channel, right? So do like the video, share the video with your friends, do subscribe to the channel as well, okay? Let me know quickly in the chats if all of you are super duper excited about tonight's particular session on chemical bonding, right? Let me know fast people, let me know fast in the chats. Let me know fast in the chats. Let me know fast in the chats, my dear people. If you all are super duper excited about tonight's session, yeah? Wonderful. So without wasting a lot of time, let's get going then. Let's get started with the first question, which is going to be on your screen in 3, 2, 1 and now. This is the first question. I'm sure every one of you can solve this particular question. We are given with following set of molecules and we need to select the one which is electron deficient. So which one is basically electron deficient among all? Is it CCl4, is it PCl5, is it BF3 or SF6? Very common question which is asked many a times, right? It's absolutely, as I can see your chats, every one of you is saying it's option C, and let me tell you it's absolutely option C which is the correct answer of this particular question. If you talk about BF3, this boron, it's forming 3 bonds over here, and right here after forming 3 bonds, it is still electron deficient because it has got just 6 electrons in its outermost shell, right, which is definitely less than that of 8, right people? So this molecule is absolutely going to be electron deficient, right? Okay, its octet is basically not complete. The octet of boron in this particular molecule is not complete. Perfect. So electron deficient molecule among all is going to be BF3. A very simple and basic question from which I started exactly. Well, if you look at all the other molecules, their octets are not incomplete basically, so they are not going to be electron deficient. Moving on to one more. Look at this particular question and let me know its answer. Which of the following pairs have zero dipole moment? Where do you see both the molecules having zero dipole moment? What do you think about this particular question, my dear people? Where do you see zero dipole moment in both the molecules? In option A, B, C or what? Well, I can see few people are coming up with option B and few are coming up with option D. So let me tell you the correct answer of this particular question is option B. Well, if you talk about SiF4, right, it has got the tetrahedral structure. Right people, this is the tetrahedral structure which it has. If you talk about BF3, it is trigonal planar like this. Right people? Every one of you would be knowing this. Well, since this silicon, it's forming some 4 sigma bonds, so its hybridization is sp3. So let me tell you, this boron, it's forming some 3 sigma bonds, its hybridization is sp2, right? These two molecules, they are perfectly symmetrical molecules. They are perfectly symmetrical molecules. All the terminal atoms are same in case of SiF4. All the terminal atoms are same in case of BF3 as well, right? Let me tell you, those molecules which are perfectly symmetric and at the same time the terminal atoms will be same, those molecules will have the net dipole moment of 0, right? So these two molecules, they'll be having net dipole moment equal to 0. So they are absolutely going to be non-polar, right? So option B is the one wherein both the molecules have got net dipole moment as 0, right? Okay, perfect guys. So it's option B which is the correct answer of this particular question. I'm sure it's clear to everyone. Let me quickly move on to one more question then. What do you think about this particular question, guys? A very simple and basic question, and I'm sure you guys can solve it easily. Among the following, the maximum covalent character is shown by which compound? Which compound shows the maximum covalent character? Which compound shows the maximum covalent character? First of all, if you look at all the examples, everywhere the anion is same. Cl negative, Cl negative, Cl negative everywhere. This is Fe di positive over here. This is Sn di positive again. This is Al tri positive. This is Mg di positive. Look at the charges on these cations. Where is the charge present on the cation maximum? In option C, the charge present on the cation is maximum. You guys must be knowing polarizing power of the cation, it is directly proportional to the charge on the ion, charge on the cation. Polarizing power of the cation is directly proportional to the charge on the cation. More the charge on the cation, more is going to be the polarizing power of the cation, and you guys know polarizing power of cation is directly proportional to the covalent character in an ionic compound, right? Perfect. Yes. So I was supposed to check which of the following has got maximum covalent character. So the charge present on the cation over here is maximum, right? So this cation will be having maximum polarizing power. If it has got maximum polarizing power as per Fajan's rules, it is going to have maximum covalent character, right? And you know covalent character, that's inversely proportional to ionic character. So this one will be having maximum covalent character, and at the same time this one will be having the minimum ionic character among all as well. Perfect. Simple and basic question. Yeah? Alright people, what do you think about this particular question? Arrange the following molecules in the increasing order of their bond angle. What do you think about this one? What do you think about this one? H2O, H2S, H2SE, H2T. These are the hydrides of group 16. You need to arrange them on the basis of their bond angle. Yeah? If you talk about water, it undergoes sp3 hybridization, right? It undergoes sp3 hybridization. Okay, if you look at the structure of water, this is basically your H2O, wherein oxygen is forming 2 sigma bonds, and there'll be 2 lone pairs on this particular oxygen. So 2 sigma, 2 lone pairs, right? Steric number is 3, so it's sp3 hybridized. So its expected bond angle was 109 degree 28 minutes, but due to the repulsions, its actual bond angle comes out to be 104 degree 5 minutes. Every one of you would be knowing this, right? 104 degree 5 minutes. If you look at all the other molecules, H2S, it is a Dragos molecule. It's a Drago molecule. And all the Drago molecules have got the bond angle approximately like less or equal to 90 degree. Right, people? All the Drago molecules, they have got the bond angle, right? Approximately 90 degree. So H2O will be having maximum bond angle among all. H2O will be absolutely having maximum bond angle among all. So it can be option 2 or option 4. Now, among H2S, among H2SE and among H2T, wherein you see the bond angle maximum among these 3 Drago molecules. Have a look exactly. If you talk about H2S, this is H2S basically, right? Wherein there are 2 lone pairs on the sulfur. If you talk about H2SE, right? If you talk about H2T, right? There are 2 lone pairs basically. There are again 2 lone pairs. There are again 2 lone pairs, right? Now people, have a look exactly. If I compare the electronegativity of this sulfur and this Se, right? Sulfur is more electronegative than Se. If sulfur is more electronegative than Se, this bond pair and this bond pair, they'll be more closer. They'll be more closer towards sulfur, right? If the bond pairs are closer, I'll say repulsions over here will be more. If repulsions are more, then definitely the bond angle in this particular case will be more than that of this one, will be more than that of this one, right? So in case of H2S, the bond angle is going to be more than that of H2SC. So this is going to be the correct answer of this particular question. It's absolutely option B, right, people? Yeah, as simple as that. Let me quickly move on to one more question then. Consider the following iodides: Pi3, ASI3, SBI3. Bond angles are given. Bond angle is maximum in case of Pi3, which is due to. What is the reason for the bond angle of Pi3 to be maximum among all? What is the reason for the bond angle of Pi3 to be maximum among all? Again, the reason is due to the bond pair repulsions. In case of Pi3, the bond angle becomes maximum as compared to all of these, right? So due to the bond pair repulsions in Pi3, the bond angle becomes maximum, right? Option B is the one which is correct. Yeah? Right, people? Moving on to one more question then. Among the following, the molecule expected to be stabilized by anion formation. Which of the following molecule will be stabilized by anion formation, right? How do we tackle this sort of equation? It's simple. Have a look. See guys, something which I would want all of you to remember from now onwards: whenever you find any 14 electron species, its bond order is going to be 3. 15 electron species, its bond order is going to be 2.5, right? 16 electron species, its bond order is going to be 2. 17 electron species, its bond order is going to be 1.5. 18 electron species, its bond order is going to be 1. Similarly, whenever you see 13 electron species, do remember 2.5 is its bond order. 12 electron species, 2 is the bond order. 11 electron species, 1.5 is the bond order. 10 electron species, 1 is the bond order. Do remember this. Do remember this first of all, okay? Now, if you are converting C2 into its anion, that is C2 negative. If you are converting C2 into C2 negative, what is happening to the bond order? What is happening to the bond order? Understand. C2, one carbon atom has got 6 electrons, so C2 has got total 12 electrons. This is 12 electron species. Now this is C2 negative. You have given 1 electron. This is a 13 electron species. So 12 electron species is getting converted to 13 electron species. 12 electron species, which has got the bond order of 2, is getting converted into 13 electron species, which has got the bond order of 2.5. So from C2 to C2 negative, when this C2 is forming the anion, is its bond order increasing or decreasing? Its bond order is increasing, and bond order is directly proportional to stability, right? If bond order is increasing, that means due to the anion formation, the stability will be increasing. So you got the first answer correct over here, right? So in case of C2 molecule, when C2 will be getting converted into its respective anion, its bond order increases, and if the bond order increases, that actually means the stability increases, right? So due to the anion formation for C2, its stability actually increases. So C2 is the one which is the correct answer of this particular equation, right, people? You can check all the other molecules over here, right? The same concept which I gave you. See, wherever due to the anion formation, bond order will be increasing, stability will be increasing at that point of time due to the anion formation. Yeah? Perfect. Let's quickly move on to one more question then. Look at this particular question. Which of the following compounds contains no covalent bond? Which of the following compounds contains no covalent bond, right? Basically, you need to see which of the following is pure ionic. Which of the following is pure ionic? It's simple. What do you think about this particular one? I can see among all the molecules there is only one compound which is pure ionic, wherein there is no covalent bond. It is basically, absolutely you all are right, it's KCl. It's KCl wherein you will be having K positive ions and Cl negative ions, right? This KCl, right, it's a purely ionic compound. There is no covalent bond as such. In all the other molecules, you will be seeing the covalent bond. For example, PH3, there are 3 covalent bonds between phosphorus and hydrogen. O2, O double bond O, 2 covalent bonds, right? Similarly, B2H6, there are some 3-centered 2 electron species, 3-centered 2 electron bonds as well. There will be 2 3-centered 2 electron bonds and 4 2-centered 2 electron bonds in case of B2H6. You guys must be knowing that, right? Those are actually the covalent bonds only. H2SO4, there are again the covalent bonds. So it's option C, only KCl is the one where there will be no covalent bond. Yeah? Perfect. Right, people? This is basically what you call as 3-centered 2 electron bond. This is what we call as 3 center 2 electron bond, or you call these two bonds as the banana bonds as well, right? This is 2 center 2 electron, 2 center 2 electron, 2 center 2 electron, and 2 center 2 electron, right? So 4 2 center 2 electron bonds and 2 3 center 2 electron bonds. And these two banana bonds, they'll be above the plane and below the plane. They won't be present on the same plane containing all the other things, right? Let me move on to one more question. This is one more question, and again a very simple one, and I would want you guys to give it a try and let me know its answer fast. Let me know fast, people. Let me know fast. I'm waiting. I'm looking at your chats only. What do you think about this one? It's a simpler one, and I'm sure you guys can solve this. You guys can solve this, I'm sure. What do you think about this particular one? I'm looking at your chats only. I would want you guys to let me know its answer in the chats. Well, some people are coming up with option C. What about the rest? What about the rest of the people? Priyadarshini is coming up with C. Akash is coming up with C. Tawfiq is coming up with D. Aisha comes up with C. Okay, look here, people, exactly how this sort of a question is to be solved. It's a simpler one. I hope you remember the structure of H3BO3. Boric acid, orthoboric acid, right? This is BOH. This is OH. This is OH. What do I need to see exactly? What do I need to see exactly? The states of hybridization of boron and oxygen atoms. Boron and oxygen atoms. We need to see the hybridization of this boron and oxygen atoms. See, all the oxygen atoms will be definitely having 2 lone pairs, right? All the oxygen atoms will be having 2 lone pairs each. Perfect. If you look at this particular boron, it does not have any lone pair, it's just forming 3 sigma bonds. So its steric number is 3. If steric number is 3, it's sp2, right? If you talk about this oxygen in particular, 2 sigma bonds, 2 lone pairs. 2 sigma bonds, 2 lone pairs. So steric number is 4. If steric number is 4, its hybridization is going to be sp3, right? So you got to know exactly the hybridization of boron is sp2 and hybridization of oxygen is absolutely going to be sp3, right? sp2, sp3 is the correct answer of this particular question. Simple, basic, right? The correct statement for the molecule CSI3. What do you think about this one? Look at all the options carefully. It's a covalent molecule. It contains CS positive and I3 negative ions. It contains CS tri-positive and I negative ions. It contains CS positive, I negative, and lattice I2 molecule. What do you think about this one? What do you think about this one? What do you think about this one? This CSI3, it's purely an ionic compound, right? It's an ionic compound. It's not the covalent molecule. Point number 1. Point number 2, what kind of ions do you have over here? Basically, this cesium, it's a group first element. Group first elements always show the oxidation state of +1, right? Group first elements always shows the oxidation state of +1. If you talk about CSI3, cesium, this I3. Cesium is the group first element, so it's going to show +1. So these 3 iodines will show -1, right? So over here, you'll be having 2 types of ions, CS positive and I3 negative. These are the 2 ions which you'll be having over here. So basically, do remember in case of CSI3, it contains CS positive and I3 negative ions. As simple as that. Option B is the one which is correct. Yeah? Right, people, it's option B. If you look at one more question, match the following and choose the correct option. You need to match the following. It's again the simpler one. Starting with SF4, right? One of the molecule I'll be showing you over. It's SF4, right? SF4. This sulfur, how many valence electrons it has? It has 6 valence electrons. How many sigma bonds this sulfur is forming? It's forming 4 sigma bonds. Out of 6 valence electrons, sulfur is using 4 of its valence electrons to form 4 sigma bonds. So there'll be 2 electrons left as such on sulfur in the form of lone pair. So 1 lone pair. 4 sigma, 1 lone pair. Steric number comes out to be 4 plus 1, that's 5. If steric number is 5, hybridization comes out to be sp3d. And which d orbital is involved in the hybridization? It's dz square. I hope you know it, right? So SF4, it's sp3d. A, you are going to join with what? SF4, you are going to join with sp3d, right? A, you are joining with 4. A, you are joining with 4. And there is only one option which says join A with 4. So option A is the one which is correct. You can check the rest of the things as well. For example, I'm talking about this NO2 positive. What is going to be the hybridization of NO2 positive? Nitrogen, how many valence electrons it has? It has got some 5 valence electrons. But there is a positive charge, so subtract this one. So 5 minus 1, 4, right? How many sigma bonds are being formed? 2 sigma bonds are being formed, right? Out of 4 valence electrons, since oxygen is divalent, right? So out of 4 valence electrons of nitrogen, all the 4 valence electrons are being consumed in forming 4 bonds over here, right? So there'll be no lone pair on nitrogen, 0 lone pair, right? Sigma plus lone pair gives you the steric number. So steric number is 2, so the hybridization is sp, right? So anode 2 positive will have the hybridization sp, so C with 3, so it's absolutely option A, which is the correct answer of this particular question, right, people? You can check the other things as well. Over here, 5 sigma, 1 lone pair, 5 plus 1, 6, sp3d2, right? 4 sigma, 0 lone pair, sp3, right? I'm sure this is clear to everyone. Let me move on to one more then. This is one more question, right? These are basically few questions based on what? Based on the dipole moment. Let's try to solve these questions as well. Look here carefully. NH3NF3, NH3NF3, right? Normally, it looks as if NF3 should have more dipole moment. It looks like that. But the case is reverse. Why is that? Have a look exactly. If you look at the structure of NH3, this is nitrogen. There is a lone pair over here, right? This is hydrogen, this is hydrogen, this is hydrogen, right? Similarly, in case of NF3, there is a lone pair right here. This is fluorine, this is one more fluorine, and this is one more fluorine. Perfect. Now guys, have a look. Nitrogen and hydrogen. Nitrogen is more electronegative, due to which the electron density will lie towards nitrogen. So this is delta negative, this is delta positive. Again, this is delta negative, again this is delta positive. This is delta negative, this is delta positive, right? So over here, the dipole moment will be in this direction, right? Due to this particular bond, the dipole moment is from positive to negative in chemistry, right? Positive to negative from here, positive to negative from here. And lone pair also contributes towards the dipole moment. Due to the lone pair, the direction of dipole moment will be towards the lone pair. So all these dipole moments are basically pointing down in the single direction. So the net dipole moment will be upwards only. The net dipole moment will be upwards only. These are basically the 4 vectors which are joining together basically, which are almost in the same direction, right? So the net dipole moment will be upwards. Okay, basically all these dipole moments are adding up. If you look at this particular case, fluorine is more electronegative, so delta negative, this will be having delta positive. So the direction of dipole moment is in this way. Similarly, due to this bond in this way, due to this bond in this way, the direction of the dipole moment due to this lone pair in this way, right? So 3 dipole moments are pointing downwards, 1 dipole moment is pointing upwards. So there will be cancellation of some dipole moment, right? Due to which the net dipole moment of NF3 will be less than that of the net dipole moment of NH3, right? Do remember this. So 1 is greater than 2. Look at the second one. Chlorine more electronegative. So delta negative, this is delta positive, right? Delta negative, delta positive. This is sp2 hybridized, this is sp2 hybridized. So this is a planar structure, right? So the direction of dipole moment due to this bond in this way, over here in this way, right? Over here this is delta negative, delta positive, so positive negative, right? Delta negative, delta positive, positive negative. These 2 dipole moments cancel out. So net dipole moment of this molecule is 0. So first will be having more than that of 2, right? Look at the next one. HF, HCl, HBr, HI. Fluorine is maximum electronegative among all these halogens, right? Fluorine is maximum electronegative. So fluorine will be having maximum charge, right? More dipole moment is basically the product of charge and distance. More the charge on the atoms, more the dipole moment. So this is going to be the order of dipole moment, right? This is going to be the order of dipole moment, as simple as that. Perfect, guys. So let's have a look on the other examples from the dipole moment only. Let's have a look exactly. If you look at the first molecule, CH3, it's electron donating group, right? CH3, electron donating, right? So this will get delta positive and over here delta negative. This CH3, electron donating, so delta positive, delta negative, dipole moment from positive to negative, dipole moment from positive to negative, both will cancel out. So net dipole moment of this is 0, right? Again, this is electron donating, so this is delta positive, this is delta negative, right? So from positive to negative over here, right? This is delta positive, this is delta negative, again from positive to negative. So one of the dipole moment is pointing downwards, one of the dipole moment is in this way, right? Okay. Similarly, if you look at this particular one, this is delta positive, electron donating, delta negative. This is going to be delta positive, this is going to be delta negative. So positive to negative, one dipole moment, positive to negative, another dipole moment, right? So one dipole moment is pointing exactly downwards, one dipole moment is pointing in this way, right? So this one has got the least dipole moment, right? This one has got the least dipole moment among all, okay? Now, these 2 dipole moments, they have got the lesser angle between them. Lesser the angle between the 2 dipole moments, more is going to be the net dipole moment. So third one is going to have the maximum dipole moment followed by 2, followed by 1, right? In the similar way, you can check out this one as well, okay? Over here, this is electron withdrawing, this is electron withdrawing, this is electron withdrawing. This is donating, this is donating, this is donating. So everywhere, this will get delta positive, delta positive, delta positive, delta negative, delta negative, delta negative. Electron withdrawing, delta negative, delta positive, delta negative, delta positive, delta negative, delta positive. So now you will be making what? You will be making the dipole moment directions, and see wherever the angle between the two dipoles will be minimum, there only the net dipole moment is going to be maximum. I'm sure this question you can solve on your own, right? I can give you this as the homework, or maybe I have given its answer as well, right? This is the answer. Moving on to one more question. In which of the following pair of molecules both the species are not likely to exist? Both the species are not likely to exist. Well. In order to check which of the following species, in order to check exactly the species which does not exist, you need to check the bond orders basically. Whenever for a molecule bond order comes out to be less or equal to 0, that molecule actually does not exist, right? Whenever you'll be having a molecule for which bond order as per the formula comes out to be less or equal to 0, that molecule actually does not exist, right? I can see HE2, it has got the 0 bond order, it does not exist, right? So this is basically the pair of species where the bond order, which does not exist basically. H2 dipositive, it does not exist, right? HE2, it does not exist, right? And if you want to see their molecular orbital configuration, you can check it out. H2 dipositive, there'll be no electron in it. If there is no electron in it, its molecular orbital configuration is sigma 1 is 0. So bond order is absolutely going to be 0. Look at this particular one, HE2, there'll be total 4 electrons. So fill these 4 electrons in these molecular orbitals. Sigma 1 is 2, sigma star 1 is 2. So 2 bonding electrons, 2 non-bonding electrons, anti-bonding electrons, anti-bonding electrons, right people? So number of electrons in bonding minus number of electrons in anti-bonding. So 2 minus 2 divided by 2 comes out to be 0. So bond order in this particular case again comes out to be 0, right? A very simple and basic question again this was. This question I'm sure you guys can solve on your own. XCF2, XCF4 and XCF6, the maximum number of lone pairs of xenon respectively. Okay, you need to calculate the number of lone pairs on xenon. If you talk about XCF2, there will be basically 3 lone pairs on xenon. XCF4, 2 lone pairs on xenon. XCF6, 1 lone pair on xenon. Why is that? Let me give you one example. See, if you talk about XCF2, this is for example your XCF2, for example, right? Now first thing, how many valence electrons this xenon has? It has 8 valence electrons. How many sigma bonds it's forming? It's forming 2 sigma bonds. How many electrons it's using for the bond formation? 2 electrons. It had 8 valence electrons. Out of 8, it is using 2. So there'll be 6 electrons left as such on xenon in the form of lone pairs. So how many lone pairs will be there? There'll be 3 lone pairs basically. So sigma plus lone pair, I think no need to check the hybridization, right? Lone pairs are 3. Perfect. So there are 3 lone pairs. Similarly, 2 lone pairs here, 1 lone pair here, right? So 3 to 1 is the correct answer of this particular question. Yeah? It's option D, which is going to be the correct one. So let's move on to one more question then. Which of the following pairs the 2 species are not isostructural? 2 species are not isostructural. Just check the hybridization of both the molecules. If the hybridization comes out to be same, they are going to be isostructural. If the hybridization is not going to be same, they are not going to be isostructural. So whenever this sort of a question comes in which you need to check which of the following pair of molecules are isostructural, just calculate their hybridization. If the hybridization comes out to be same, they are going to be isostructural. If not, they are not going to be. For example, CO3 dinegative, NO3 negative. If you talk about CO3 dinegative, right? Carbon, how many valence electrons it has? 4 valence electrons. There is a dinegative charge, so 4 plus 2 comes out to be 6. How many sigma bonds it's forming? It's forming 3 sigma bonds, right? 3 sigma bonds because 3 terminal atoms are attached. Number of terminal atoms always equal to number of sigma bonds. Do remember that, right? Now oxygen being divalent. So how many lone pairs will be there? Out of 6 valence electrons, this carbon will be using all its 6 electrons to form bonds, right? So there'll be no lone pair as such. Sigma plus lone pair. 3 plus 0 comes out to be 3. The steric number is simply going to be, the hybridization is going to be sp2. Similarly, if you talk about, or if you look at the structure of it as well, this is C double bond O, this oxygen carrying negative, oxygen carrying negative. So 1, 2, 3, 3 sigma bonds, 0 lone pair, it's going to be sp2, right? In case of NO3 negative, nitrogen, its valence electrons are actually 5. There is a negative charge, so 5 plus 1, 6. How many sigma bonds? Since there are 3 terminal atoms, so 3 sigma bonds. How many lone pairs on nitrogen? Out of 6, all the 6 are used because there's a divalent over here. So lone pair is 0. 3 plus 0 is 3. So sp2 hybridization. So these two have got same hybridization. So they'll be absolutely isostructural. But if you look at this one, phosphorus. Over here, 5 sigma bonds, 0 lone pair on phosphorus, right? 5 plus 0, 5 sigma bonds, 0 lone pair. 5 plus 0, 5. Steric number 5, sp3d, right? BRF5, 5 sigma bonds, 1 lone pair on bromine. 5 plus 1, 6. Steric number 6, sp3d2. So in this particular case, the hybridization is different, so they are not going to be isostructural. Absolutely, it's option C, which is the correct answer of this particular question. So basically, you need to simply check the hybridization. If the hybridization is same, they are going to be isostructural, right? Look at the next one. Among the following, the linear species is. Which of the following is linear? These are all the common examples. NO2, this is bent shaped. Cl2O, this is again bent. O3 again bent. N3 negative is the only one which is linear. If you want to have a look on their structures, just have a look on their structures as well. These are very, very common examples, right? This NO2, odd electron species, right? It's bent. Cl2O, it's again bent, like water shape, right? O3, again bent. N3 negative is the only one which is linear among all. I'm sure this sort of a question you can, and do remember these examples. These are frequently asked, right? These are frequently asked, okay? And one more example, that is I3 negative. That's also asked, right? I3 negative, that's also linear, right? Do remember that as well. Look at this particular one. The molecular shape of SF4, CF4 and XCF4 are different or same? Different or same? Same. SF4, it's a very common molecule, right? It has got the seesaw shape, you guys must be knowing, right? Because it has got 4 sigma bonds and 1 lone pair on sulfur. 4 sigma bonds, 1 lone pair. It is of the type AB4L1. It has got seesaw shape. CF4, right? 4 sigma bonds, it's tetrahedral. XCF4, 4 sigma bonds, 2 lone pairs, it's square planar. So their shapes are basically different. Their shapes are basically different, right? If you talk about SF4, this is sulfur, right? This is sulfur over here, right? This is sulfur, this is sulfur over here. Sorry, there is 1 lone pair, right? There is 1 lone pair. This is sulfur, perfect. This is 1 lone pair over here. This is fluorine, this is fluorine. These 2 fluorine atoms are present on the equatorial plane, right? On the axial plane, there will be 2 more fluorine atoms, right? These are 2 fluorine atoms, so the shape becomes seesaw type. Neglect this lone pair. Remove this lone pair over here. It looks like seesaw, perfect. Similarly, CF4. CF4 has got perfect tetrahedral shape, right? Right, people? This is CF4. Similarly, XCF4. This is xenon, it's square planar. This is fluorine. 1 more fluorine over here. This is 1 more fluorine. 1 more fluorine, right? Perfect. So these 4 fluorine atoms with the xenon, they are present on the equatorial plane, right? There is a lone pair present on the axial plane over here. 1 more lone pair present on the axial plane. So this is square planar, right? So basically, their shapes are different. There is 1 lone pair on sulfur, 0 lone pair over here. 2 lone pairs, 1, 0, 2 lone pairs, 1, 0, 2 lone pairs, different with 1, 0, 2 lone pairs, right? So option A is the one which is going to be the correct answer of this particular question, right? Yes? Let's have a look on one more. The hybridization of orbitals of nitrogen in NO3 negative, NO2 positive, NH4 positive. So first of all, have a look on this NH4 positive, people. Have a look on this NH4 positive, right? If you talk about this NH4 positive in particular, nitrogen, how many valence electrons? 5. There is a positive charge, so subtract this 1, so it comes out to be 4. How many sigma bonds? The number of terminal atoms always gives the number of sigma bonds. So all the 4 valence electrons have been used to form the 4 sigma bonds, so there will be no lone pair. If there is no lone pair, steric number 4 plus 0 comes out to be 4, so the hybridization is sp3. So in the last case, the hybridization is sp3. sp3, right? So now have a look on NO3 negative. If you have a look on NO3 negative, right, I can calculate its hybridization in a similar way, right? See guys, nitrogen, it has got how many valence electrons? 5. There is a negative charge, so 5 plus 1 comes out to be 6. How many sigma bonds? 3 sigma bonds. The number of terminal atoms always gives the number of sigma bonds, right? Now oxygen being divalent, so all these 6 valence electrons will have been used, right, as per the rule which we use over here. So there will be no lone pair on nitrogen. So 3 plus 0 comes out to be 3. Steric number is 3, so it's going to be sp2, right? So it's sp2. So this sp2, right? So there is no option, right, which resembles with this one. So it's option A only, which is going to be the correct answer of this particular question, right, people? Again, the simpler one this was. Let's move on to one more. Just a second. What? Oh, I was checking for NO3 negative. Was I checking for NO3 negative? NO3 negative was sp. What it was? Was it sp2, right? It was sp2. Okay. Exactly, guys. This is the option, right? We got this one only. Perfect. We got this one only. I was checking for NO3 negative, right, which came out to be sp2. So there is this option. This is sp2 over here. So it's option 2. Yeah. Same procedure which I gave you. Which of the following order of energies of molecular orbitals of N2 is correct? Which of the following energies, right? How do you fill the molecular orbitals? How do you fill electrons in the molecular orbitals, right? For what? For N2 molecule. What do you think? Which one is correct? Can you let me know in the chats fast? Let me know in the chats fast, people. Looking at your chats only. Which is the correct order of filling of electrons in the molecular orbitals for nitrogen? Nitrogen, guys, nitrogen. Nitrogen. Vijit is coming up with option C. What about the rest? It is going to be option A, my dear people. This is the sequence in which the electrons are to be filled in what? In N2 molecule, right? There are two sequences basically for the species which have got the electrons less than 14, and then for the electrons for the species which have got the, right, greater than 14. So this is basically the correct sequence which is to be followed for the nitrogen for the electron filling in case of this, I mean in its molecular orbitals, right? You can calculate its bond order as well. Number of electrons in bonding molecular orbital minus antibonding divided by 2, its bond order will eventually come out to be 3, right? It has got 2, 4, 6, 8. 8 electrons in its bonding minus 2 anti-bonding. 8 minus 2 comes out to be 6. 6 divided by 2 comes out to be 3. So there only its bond order comes out to be 3. And N2 molecule, let me tell you, it's perfectly diamagnetic. There is no unpaired electron in the molecular orbital as such. It's perfectly diamagnetic, right? It's not going to be paramagnetic. Among the following species, the diamagnetic molecule is, okay, which of the following is diamagnetic? CO, carbon monoxide. 8 electrons in oxygen, 6. 8 plus 6, 14. It's a 14 electron species. 14 electron species means it is same as the nitrogen. Few minutes back only I've told you this is diamagnetic, right? It does not have any unpaired electrons. So this is the answer, right? It's done. Among the following, the diamagnetic molecule is, few minutes back only we saw, right? N2, which was the 14 electron species. Carbon monoxide, again the 14 electron species. Isoelectronic species, they have got the same bond order. They have got the same, they show the same magnetism as well, right? So if N2 is diamagnetic, that means the CO must be also diamagnetic, right? Simple. So option A. In all the ones, if you write their molecular orbital configurations, absolutely they will be having the unpaired electrons, right? Like oxygen. Oxygen will be having 2 unpaired electrons in its molecular orbitals, right? Right? Pi star 2pxy, pi star 2py1, right? So there'll be 2 unpaired electrons in basically oxygen. As you can see, pi star 2px1, pi star 2py1, 2 unpaired electrons, so it's going to be paramagnetic. NO, there is 1 unpaired electron. B2, there are 2 unpaired electrons, right? Wherever there will be unpaired electrons in the molecular orbitals, absolutely that's going to be paramagnetic, right? Carbon monoxide, there won't be any unpaired electron, as you can see over here. There is no unpaired electron as such, so it's absolutely going to be diamagnetic, right? Simple. So basically you need to know how to write the molecular orbital configurations of different species, right? Eventually fill the electrons as per the increasing order of energies. So that species where the molecular orbitals will be unpaired, that's going to be para. Where the molecular orbital will be paired, that's going to be diamagnetic, right? The number of species below that have 2 lone pairs of electrons in their central atom. Which of the following has got 2 lone pairs of electrons in their central atom? Sulfur, it has got 1 lone pair. Few minutes back only we have saw its shape is seesaw, 4 sigma bonds, 1 lone pair. Bf4 negative, there'll be no lone pair as such. There'll be no lone pair on boron as such. ClF3, see there are 7 valence electrons, right? Out of 7 valence electrons, 3 valence electrons are used to form 3 sigma bonds. So there'll be 4 valence electrons as such in the form of 2 lone pairs, right? Yes. AsF3, right? Arsenic, it belongs to group 15, right? So there'll be 1 lone pair on arsenic. Perfect, because it has got 5 valence electrons, 3 it is using, right? So 2 electrons as such, so 1 lone pair. PCl5, no lone pair. BrF5, there'll be 1 lone pair on bromine. XCF4, there'll be 2 lone pairs on xenon. 2 lone pairs on xenon. SF6, no lone pair on sulfur. So how many molecules do we have where the central atom has got only 2 lone pairs? Have a look. This has got only 2 lone pairs, 2 lone pairs, 2 lone pairs. So there are only 2 molecules among all where the central atom has got 2 lone pairs. So 2 is going to be the answer of this particular question, right? You can look at their structures as well. Perfect. You guys can easily draw them, I'm sure. Yeah. This is going to be seesaw. This is going to be tetrahedral. ClF3, 3 sigma bonds. 3 sigma bonds, 2 lone pairs, right? 3 sigma bonds, 2 lone pairs, T-shaped. ASF3, 3 sigma bonds, 1 lone pair, pyramidal. 5 sigma bonds, 0 lone pair, perfectly trigonal, bipyramidal. BRF3, 5 sigma bonds, 1 lone pair, square pyramidal, square planar, octahedral, right? Easily, the structures are given to us. The structure of IF7, 7 sigma bonds, 0 lone pairs. 7 plus 0, steric number is 7, sp3d3, pentagonal bipyramidal, right? Pentagonal bipyramidal, IF7, a very common example. Yeah? Which of the following statement is correct? Which of the following statement are correct? In the formation of dioxygen from oxygen atoms, 10 molecular orbitals will be formed, okay? All the molecular orbitals in the dioxygen will be completely filled. No way, because few minutes back only we saw the molecular orbital configuration of oxygen. There'll be 2 molecular orbitals wherein there was one electron present, right? Where there were unpaired electrons present. So this one is incorrect. Total number of bonding molecular orbitals will not be same as the total number of anti-bonding orbitals in dioxygen. Incorrect, right? When 2 atomic orbitals combine, they lead to the formation of 2 molecular orbitals, right? They lead to the formation of 2 molecular orbitals. As per LCO, linear combination of atomic orbitals is concerned, number of atomic orbitals combining is always equal to the number of molecular orbitals formed, right? And out of the molecular orbitals which get formed, out of them half will be bonding, half will be anti-bonding. So this is incorrect. Number of filled bonding orbitals will be same as that of, this one is also incorrect. So the correct answer is basically option A, right? So basically, if you talk about the oxygen configuration, oxygen outermost configuration, oxygen configuration, it's going to be 1s2, 2s2, 2p containing 4, right? So this is 1s orbital, this is 2s orbital, and 2p containing 4, right? 1, 2, 3, 4. So how many orbitals in total we have? 1, 2, 3, 4, 5. So 5 orbitals, right? So one more oxygen will have 5 more orbitals. So 5 and 5, 10 orbitals are basically combining. They'll lead to the formation of 10 molecular orbitals, out of which 5 will be bonding, 5 will be anti-bonding, right? So option A is the correct answer of this particular question. Right, people? Again, the simple and basic question this was. Right? You can check it out too. This is the molecular orbital configuration of oxygen, O2. In accordance to molecular theory, O2 positive is diamagnetic, bond order is more than O2. Let's check it out. Few minutes back only I had given you one simple result. 14 electron species will be always having bond order of 3. 15 electron species will be having bond order of 2.5. 16 electron species will be having bond order of 2. 17 electron species will be having bond order of 1.5. 18 electron species 1. Right? Now, O2 positive. How many electrons are there in O2 positive? O2 positive. 1 oxygen 8 electrons, 2 oxygen 16 electrons, and there is a positive charge 16 minus 1 15 electrons. So O2 positive is a 15 electron species, right? This is a 16 electron species. So O2 positive is diamagnetic. O2 positive is diamagnetic. Is that? See guys, let me tell you, O2 positive it is a 15 electron species and O2 is a 16 electron species. In case of O2 there are 2 unpaired electrons. In case of O2 positive there will be 1 unpaired electron, right? So both are basically paramagnetic. Both are paramagnetic. O2 positive is diamagnetic. This one is wrong. O2 positive is diamagnetic. This one is wrong. O2 positive is paramagnetic. Absolutely. And its bond order is more than that of O2. Is the bond order of O2 positive more than that of O2? Right? Correct. So option C is the one which is the correct answer of this particular question. Right? Again, the simpler one. Yeah? Okay. Moving on to one more. Using molecular orbital theory, predict which of the following species has the shortest bond length. See. More the bond order, lesser the bond length. So bond order is basically inversely proportional to bond length, right? Which electron species this is? 8 at 16 minus 2. This is a 14 electron species. This one, 8 at 16 minus 1, 15 electron species. 8 at 16 plus 1, 17 electron species. 8 at 16, 18 electron species. 14 electron species always has the bond order of 3, right? 15 electron species, 2.5. 16 electron species, 2. 17 electron species, 1.5. 18 electron species, 1. So where is the bond length minimum? Wherever bond order is maximum, bond length will be minimum. Bond order is maximum here, so bond length will be minimum here. So O2 positive is the one which is correct. Right guys, I'm sure you can easily solve this one. Okay. Orthonitrophenol is less soluble in water than that of paranitro or metanitrophenol. Why is that? Orthonitrophenol is less soluble, which is absolutely correct. Orthonitrophenol is less soluble in water than that of paranitrophenol and metanitrophenol. Why? Because in case of orthonitrophenol, intramolecular hydrogen bonding happens, right? Hydrogen bonding in the molecule itself, right? Yes, due to the intramolecular hydrogen bonding in orthonitrophenol, which is what makes it less soluble in water as compared to para and metanitrophenol, right? So basically orthonitrophenol undergoes what? Intramolecular hydrogen bonding. So it's option B, which is the correct molecule. Hydrogen bonding within the molecule means intra, hydrogen bonding between two molecules means inter, right? But in this particular case, intramolecular hydrogen bonding occurs, right? Okay, the number of types of bonds between two carbon atoms in calcium carbide. If you talk about calcium carbide, CaC2, common example, what is its structure? This is C, this is triple bond, this is calcium, this is CaC2, right? What the question says, the number of types of bonds between two carbon atoms. Between two carbon atoms, there are two types of bonds. This is sigma and these two are pi, right? 1 sigma, 2 pi bond. 1 sigma, 2 pi bonds. First, this is sigma and these two are pi, right? So it's option A only, simpler one. Just remember its structure, that's it, CaC2. Okay, among the two OH bonds in H2O molecule, the energy required to break the first OH bond and the other OH bond is same. Absolutely incorrect, right? It's not the correct statement. The energy needed to break first OH bond and the second OH bond, they'll be absolutely different. Right? This is because the electronic environment around oxygen is same even after the breakage of OH bond. No, this again wrong. The reason is why the first OH bond energy and the second OH bond energy in case of water is different. The reason is the electronic environment around the oxygen is not same. Even after the breakage of the first OH bond, right? That is the actual statement. So both the statements are absolutely false. Both the statements are not correct. Yeah? Both the statements are not correct. Which of the following pairs of species have same bond order? Again, the similar sort of question, right? What do you think about these questions, guys? What is going to be the correct answer of this particular? I've solved many questions of this format. I want you guys to let me know its answer now. See, carbon 6 electrons, nitrogen 7. 7 plus 6, 13, 13 and negative charge, 13 plus 1, 14. It's a 14 electron species. This one is also 14 electron species. And all the 14 electron species, they have got the bond order of 3, right? So they have got the same bond order. They are going to be diamagnetic, right? Option A. In which of the following ionization process the bond order has increased and the magnetic behavior has changed? Again, this similar sort of question. Again, this you'll be writing their molecular orbital configurations and calculating the bond order exactly, and you'll exactly see where the bond order has increased and where the magnetic behavior has changed, right? So have a look on its solution. These are basically the molecular orbital configurations which are mentioned over here, right? Which are mentioned over here for NO and NO positive and NO negative as well. This is NO negative, right? Okay, these sort of questions we have solved a few minutes back only. Write their molecular orbital configuration, use the bond order formula, number of bonding minus number of anti-bonding divided by 2, right? You'll be getting the bond order and then eventually you can solve these sort of questions. We have solved many sort of questions like this, okay? The sum of lone pair of electrons in each of the central atom in the following, right? And I've already shown you how to calculate the lone pairs on the central atom as well. Perfect. And I'm sure you can solve this question again on your own. Or if you just remember the structures, their structures are like this. Have a look. This is your SNF3, right? Sulfur has used all its 6 valence electrons to form 6 bonds over here. So there is no lone pair on sulfur, right? Te, how many bonds it's forming? 1, 2, 3, 4, 5, 6, right? How many bonds? Wait, it is TF6. Just a second, guys. It is basically TeBr6, right? TeBr6 dinegative. This tellurium, it belongs to oxygen family, right? 6 plus 2, 8 valence electrons, right? Out of 8, 6 are being used, so there will be 1 lone pair, right? So 6 sigma bonds, 1 lone pair, right? BrF2, similarly you can calculate the bond pairs, you can calculate the lone pairs over here, right? 7 valence electrons, but there's a positive charge, so 7 minus 1, 6. Out of 6, 2 are being used, so 4 electrons will be left as such on bromine in the form of 2 lone pairs, right? SNF3 we have checked, XCF3 negative. So 8 plus 1, 9, out of 9, 3 are used, 6 will be as such in the form of 3 lone pairs in case of xenon, right? You can easily solve these sort of questions and I've already shown you how to check the number of lone pairs. In which of the following molecules all the bonds are not equal? It is basically SF4, which has got the seesaw shape, where sulfur has got one lone pair, right? It is basically SF4 where all the bond lengths are not going to be same, right? Sir, can you explain SNF3? This is the structure of SNF3. Sulfur, how many bonds it's forming? 3, 4, 5, 6. 6 bonds it's forming. Sulfur has got 6 valence electrons. Out of 6 valence electrons, it is using 1, 2, 3, 4, 5, 6. It is using all its 6 valence electrons to form 6 bonds, right? So there'll be no electron left as such on sulfur, so no lone pair on sulfur. Yeah? I'm sure it's clear. SF4 is going to be the answer of this particular question, right? Hybridization of highlighted atom chains in. Wherein do you see the hybridization chains for the highlighted atom? Aluminium, it is forming 3 sigma bonds, right? It's forming 3 sigma bonds, no lone pair, so sp2, right? AlH4 negative, it's forming 4 sigma bonds, it's sp3. So in the first one only the hybridization is changing. In case of water, hybridization of oxygen is going to be sp3, 2 sigma, 2 lone pairs. Over here, again it's going to be sp3 only, right? NH3, sp3, NH4 positive, sp3, right? So first one is the one wherein the hybridization changes exactly. Yeah? Right, people? A covalent molecule AB3 has pyramidal shape, the number of lone pairs and bond pairs. Again, simple AB3, like NH3 molecule. In case of NH3 molecule, there are 3 sigma bonds and 1 lone pair. 3 sigma bonds, 1 lone pair. AB3L1 type. It's going to be pyramidal, right? 3 sigma bonds, 1 lone pair. Yeah? 3 sigma bonds, 1 lone pair. So 1 lone pair, 3 sigma bonds. Perfect. Bond strength. Arrange them on the basis of their bond strength. Again, the similar sort of question. This is a 16 electron species. This is 17 electron species. This is 18 electron species. This is 15 electron species, right? 16 electron species has got the bond order of 2. 17 has got 1.5. 18 has got 1. And 15 has got again what? 15 electron species has got the bond order of 1.5. Correct? Correct, people? So wherever bond order is maximum, there only bond strength is maximum. Bond order is maximum in O2. So bond strength will be maximum in O2. Right? In O2, the bond strength is going to be maximum. Perfect? So there is only one option which says the bond strength of O2 is maximum, right? Which is this one. Perfect? Or wait, just a second. This is not 1.5, right? See, 14 electron species has got the bond order of 3, right? So 15 electron species has got the bond order of 2.5. So basically it's O2 positive where the bond order is maximum. If the bond order is maximum, what is going to happen? Its bond strength is going to be maximum. O2 positive will have the bond order of maximum. And its strength will be maximum as well. O2 positive, its bond order is 2.5. So it's option D which is the correct answer of this question. It's D which is the correct answer of this particular question, right? I'm sure you can easily solve this, right? And with these questions, I'm sure a lot of concepts from the chapter chemical bonding would have been done and dusted. Right, people? Okay, perfect. At the same time, let me just tell you one quick thing. If you have not enrolled into the Vedantu JEE crash course batch yet, do get enrolled in it as soon as possible, my dear people, because this is the last option for you guys to cover your whole syllabus on time in just this 1.5 months. Apart from that, we are going to train you through test series only, test series as well, right? There will be chapter-wise assignments. There will be chapter-wise assignments which you guys are going to solve. Chapter-wise tests will be there, by which are going to make you exam friendly at the same time, by means of which you will get to know what to study, what not to study, right? Okay, whatever things are required basically for JEE examination to get qualified, all those things are incorporated in this particular crash course batch, right? Okay, so do get enrolled into the JEE 2022 crash course batch as soon as possible, because in this particular crash course batch, the best teachers of Vedantu will be training you in all the 3 subjects, that too on actual Vedantu platform. You'll be getting the personal care from the teachers, right? You'll be getting the study material from our side, right? Test series, no need to buy from some other source. Test series will be free of cost, right? Study material will be free of cost. Every single thing which is needed for you guys right now to ease out your preparation, to prepare well, right? All those things are basically included in this, yeah? And it's completely People, affordable. These are the features of this particular crash course which I'm talking about, right? So there'll be full syllabus revision, right? There'll be 10 full tests and 10 part tests, right? Chapter-wise assignments by means of which you can compare your ranks with the other students across the country, right? Unlimited doubt solving, summary notes, class recordings, right? Key concepts, important formula sheets, every single thing which is needed for the JEE to get cracked, all those things are included in this one, right? And people, it's completely affordable. In 8K, using this coupon code WBJCC, you'll be getting enrolled in this particular crash course batch. Link is there in the description box of the video. Let me quickly show you how to get enrolled in this particular crash course batch. See, this is the video which you guys are currently watching. Just drag it a little down, click on show more. After clicking on show more, click on this particular link, JEE crash course. Well, after clicking on JEE crash course, just drag it a little down, right? Click on buy now. After clicking on buy now, you need to put your number or email ID on which you will be getting the OTP, and eventually you will be getting enrolled into the JEE 2022 crash course batch, which is starting on the actual Vedantu platform, right? So do it as soon as possible in order to shoot up your ranks in the JEE Mains examination. Trust me, it's my personal and the honest suggestion for you guys to shoot up your ranks, because majority of the selections in Vedantu are actually from the crash course batch only, right? You would have seen the last year result as well, right? In the first top 10,000 ranks in JEE Mains, among the first top 10,000 ranks in JEE Mains, there were 983 students from Vedantu, among the top first 10,000 ranks, right? And majority of them were actually from the crash course batches only. So basically, the master teachers who train you in the crash course, they have got the teaching experience of more than 15 to 20 years, right? More than that, they actually know what to teach, what not to teach. Perfect. So they will be completing your whole syllabus in all the 3 subjects in just this 1.5 months, right? Apart from that, test series, study material, right? Chapter-wise assignments, class recordings, summary notes, handwritten notes, right? Every single thing will be provided to you. So basically, we are going to train you personally on the actual Vedantu platform. So do get enrolled as soon as possible, and let me know in the comment section of the video if you'll be having any sort of query related to the crash course, right? So with this, people, I'm going to take a leave. I'll see you guys tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all. Take care, guys. Bye.